Let's get started, okay, with today's class. So today what we will do is consider a case study. Like we will start from deriving the equation of motion, deriving the transfer function, and then like using that to design controllers to satisfy performance and stability, and then we will also look at how to construct the root locus and use the root locus for designing the controller, right. So ultimately we go through the entire control design process for an example system, right. So that's something which we will start off today. So the system that we are going to consider is a gear transmission, which is pretty common in many practical systems today, right. So let's say we have an input gear that has N1 teeth on it, right, and that is meshed with an output gear which has N2 teeth on it, right. So we have the input shaft, to which an input torque of Tm is given to it. Like for example, this input torque could come from a motor, right, which is driving the input shaft, right. So and that input torque is going to drive the entire shaft and gear assembly. Let us say that the moment of inertia of the entire input shaft and input gear assembly put together is some J1, right, and the input shaft is supported on a bearing with a friction coefficient of F1. So the viscous friction coefficient is F1. That means that the frictional torque which is dissipated is essentially F1 times omega 1. Right. So that is the implication of that coefficient F1, right. So and similarly the of course the angular displacement of the input shaft is, let's say, theta 1 t, right. The angular displacement of the output shaft is going to be theta 2, and J2 is the moment of inertia of the output shaft assembly along with the output gear, right. F2 is the corresponding friction coefficient, right, for the output gear. So consequently the torque which is essentially used up in overcoming friction of the output shaft is going to be F2 times omega 2, right. So that's the viscous friction coefficient, and let's say like we have a load torque TL, right. Obviously the output is going to drive some load, okay. See, for example, one could essentially use this arrangement to, let's say, drive the wheel of a vehicle, right. So let's say you have a wheel of a car which is loaded, so it will basically provide some resistance, right. That is a load torque, okay. So we finally need to overcome the load torque and operate the output shaft at a desired state, right. So the first step is for us to essentially derive the governing equation of motion, okay. So we are going to essentially consider this entire entity as a system to which we provide the torque TMT as the input, and the angular displacement of the output shaft theta 2t is the output, okay. So that is the visualization. Of course this is because ultimately we are going to look at position control, right. So that is the objective that we are going to look at here, right. Let's say I want to control the angular displacement of the output shaft, how do I do that, okay. Of course we alternatively we can also do consider the output to be omega 2t, okay, wherein I want to do speed control of the output shaft, right. I would do position control, I would leave speed control to you as a homework, right. So but that's going to be pretty straightforward, at least the derivation of the transfer function is going to be pretty straightforward, right, once we do this derivation, right. The controller part needs to be redone. So so let us first derive the governing equations of motion, okay. That is the first task that we are going to do. So let's get started with that, okay. To do that, let's draw the free body diagram of the input shaft, right. So let's first draw the free body diagram of the input shaft, then let's write down the corresponding equation of motion. So let's say I draw the input shaft. Okay. So what are all the torques that are going to act on this input shaft? So essentially we have the input torque TMT is acting. Okay. So are there some resisting torques? Yes, there are, right? So we have one due to friction, which is F1 times theta 1 dot T. Okay. And would there be any other torque which would be essentially in a sense resisting the motion of the input shaft? Please note that the input shaft is driving the output shaft, right? So obviously the output shaft is going to exert a reaction, right, for the action that the input shaft does on the output shaft, right? Let's say we call this reaction torque as some T1T. Okay, so T1T is essentially the reaction torque from the output shaft to the input shaft due to the fact that the input shaft is driving the output shaft, right? So these are the torques that are acting on the input shaft, right? So if we write down the equation of motion, so what's going to happen? So J1 times theta 1 double dot T, that's going to be equal to the net torque which is acting on this body, right? That's going to be the input torque TMT minus F1 theta 1 dot T and then minus T1T. Okay, so that's what we are going to have, right? So just rearranging these terms, we will get the equation as J1 times theta 1 double dot T plus F1 theta 1 dot T is equal to TMT minus T1T. Okay. So let's call this as equation number 1, right? So that is the governing equation for the input shaft. So similarly, let's draw the free body diagram for the output shaft and see what happens, right? So if I draw the free body diagram for the output shaft, what's going to happen? I am going to get this. Right. So as far as the output shaft is concerned, like I need some torque to drive the output shaft, right? So let's say we call that driving torque as T2T, right? That's what comes from the input shaft, right? So essentially that is the driving torque, right? So as far as the output shaft is concerned, and what are the resisting torques? Like we are going to have a friction torque F2 times theta 2 dot T, and of course the load torque is an torque which is going to essentially resist the motion of the output shaft, right? So that's going to be another thing, right? So what we are going to have essentially is J2 dot theta 2, J2 times theta 2 double dot, that's going to be equal to T2T minus F2 theta 2 dot T minus TLT, right? That's going to be the governing equation. So just rearranging the terms, like we get the equation as J2 times theta 2 double dot plus F2 times theta 2 dot, that's going to be equal to T2T minus TLT. Okay, so let's call this as equation number 2. Okay, so those are the two equations, right? Now, of course, we need to eliminate T1, T2, and theta 1, right? Because ultimately we want one consolidated equation relating the output to the input, right? So if you recall, that's what we are aiming for, right? So as far as our framework is concerned, ultimately if we identify a system with an input and an output, we want a governing linear ODE that relates the input to the output, right? So our input is Tm, output is theta 2. So we should have an ODE only relating those two variables, right? TLT, one can model it as a disturbance, okay? So we'll come to that later. So but then let's try to see how we can eliminate it. Now, please note that N1 and N2 are system parameters, right? So, the input gear has N1 teeth and the output gear has N2 teeth, right? Can we use this information to relate theta 1 and theta 2? Assuming that there is no slip at the gear interface, like how are theta 1, theta 2, N1, N2 related? What will be the relationship between the variables theta 1, theta 2 and N1 and N2? See, of course, there are various ways to look at it. Like see, if two gears are in meshing or in mesh with each other, like essentially the pitch should be the same, right? Then only they will mesh with each other, right? Using those ideas, one can easily get an relationship. I will write down the relationship. You think about it as homework, okay? So you figure it out as to how we can get it, okay? So immediately one can note that essentially theta 2t divided by theta 1t, that's going to be equal to N1 by N2, okay? So that's what we are going to have. Okay. So, there is going to be a relationship between the angular displacements and the number of teeth in the two gears in this manner. Okay. So, that is what we are going to get as far as this gear is concerned. And of course, if once we have this, like we want to essentially eliminate theta 1. So, what you can immediately see that is the following: theta 1 is going to be equal to N2 by N1 theta 2t, right? Correct, from this equation. So, this implies that I can write theta 1 dot as N2 by N1 theta 2 dot, right? Similarly, I can write theta 1 double dot is going to be equal to N2 by N1 theta 2 double dot, right? We can write all these equations, right? So, once we figure this one out, correct? Okay. So, that takes care of theta 1, right? So, I can eliminate theta 1 from theta 1 double dot and theta 1 dot from equation 1. But now I need to figure out what to do with T1 and T2. Is there a relationship between T1 and T2? Yes, there is, right? Because energy should be conserved, right? When essentially the system is operation, right? So, if we consider the interface, like, so of course we will make an assumption that we neglect energy losses. Okay, of course, if we do not neglect energy losses, typically we need to put an efficiency term. Okay, like so, neglecting energy losses, we can immediately see that T1 T1t theta 1t, that is the work done by the input shaft, right? That is going to be equal to T2t times theta 2t, right? That is going to be the what to say energy balance of the gear interface, right? The gear mesh. Okay. Of course, if we want to take into account energy loss, what we can do is that here I can multiply by a efficiency term, a transmission efficiency. Okay. So, that means that because output there is going to be some energy dissipation at the what to say gear interface due to friction and so on, right. So, what to say it is not perfect, right. So, what we will have is that like we may have some frictional losses, but for the time being we will neglect them, right. So, essentially, but if someone wants to incorporate it, you multiply the factor theta, the term T1t theta 1t with an efficiency eta t, and that is going to be equal to the energy term T2t times theta 2t, right. So, but for the time being we will consider eta t to be 100%, okay, just for simplicity, okay. But if someone gives us this parameter, we can of course incorporate it, okay. That is what I just wanted to convey through you. right. So, this one, this is T1 T times theta 1 T, okay. So, this immediately tells us, what does this tell us? This immediately gives us that T1 T theta 1 T divided by theta 2 T is equal to T2 T, okay. This immediately gives us that T2 T is going to be equal to T1 T, okay, N2 by N1, right. Why? Because theta 1 by theta 2 is N2 by N1, okay. So, that is how we get this relationship, okay. Now, we are all set, okay. So, now let us go back to equation number 1, okay, and let us say we take equation number 1 and multiply both sides by N2 by N1, okay. Let us take equation number 1, let us multiply both sides by N2 by N1, I can do that, right. So, then what will I get? I will get J times, J1 times N2 by N1 theta 1 double dot T plus F1 theta 1 dot T, that is going to be equal to TMT minus T1T N2 by N1, okay. That is what I will get, right, after once I multiply by N2 by N1 on both sides, right. So, now I plug in for substitute for theta 1 double dot and theta 1 dot, right. So, if I substitute for theta 1 double dot is going to be N2 by N1 theta 2 double dot, right. So, let us substitute there. So, what will happen? This will become N2 by N1 whole square theta 2 double dot, right. So, that is what is going to happen here, okay. Of course, I think I missed an N2 by N1 here, right, because obviously, like I am multiplying both sides by N2 by N1, right. Even F1 should be multiplied by N2 by N1, right, sorry about that. Yeah, even TMT, right. So, okay, sorry about that, right. So, of course, equation 1 I am multiplying both sides by N2 by N1, I think I missed those two terms, sorry. So, consequently, if I substitute for theta 1 dot, this is going to be F1 times N2 by N1 whole square theta 2 dot, okay, and that is going to be N2 by N1 TMT minus T2T. Do you agree? Why did I get T2T? Because T2T is T1T times N2 by, right. So, that is why we have this, right. Now, we are almost through, okay. So, what do? We just add 2 and 3, okay. So, let us say like let us do 2 plus 3. So, what will 2 plus 3 give me? It will give me J1 N2 by N1 whole square plus J2 theta 2 double dot T plus F1 N2 by N1 whole square plus F2 theta 2 dot T, that is going to be equal to N2 by N1 TMT minus TLT. Okay. So, this is the governing equation of motion, okay, for this gear transmission system, right. So, you see that we have in the form that we want, right. So, That is, we want on the left hand side the output and the derivatives, right hand side we want the input and the derivatives, right. But if you look at the right hand side, we have the input TMT and TLT, you know, like as I told you, TLT is an input which comes into the system, but we can treat it as a disturbance, right. So, because we need to overcome it, right, is it not correct. So, we give a load torque, essentially I need to overcome that load torque, right. I need to apply an input which will overcome that. Okay. So, that is something which we need to account for. Okay. So, I hope this is clear, right, until this point.